Welcome to the Incremental Block-Based Compilation online training. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this training, you will learn about incremental block-based compilation, the idea of dividing an FPGA design into pieces called design partitions, and performing compilations that can reuse the previous compilation results from each partition. This allows you to lock down the achieved performance of subdesigns in your project, making it a very useful tool for closing timing on a design. You'll learn how to create design partitions and some best practices for their creation that will provide the most benefit when performing an incremental block-based compilation. Here's the agenda for this training. In the previous parts of this training, you were introduced to incremental block-based compilation and design partitions. You learned about preparing your design for incremental block-based compilation and some guidelines on how to create good design partitions. You also learned about the tools in the Intel Quartus Prime Pro Edition software that support the creation and management of design partitions. In this final part of the training, you'll learn some useful tips and tricks for what you can do with design partitions and a few useful techniques for closing timing using this feature. Now let's look at some additional tips and techniques you can use when working with design partitions. Now that you know about incremental block-based compilation, design partitions, and the tools used to work with them, what do you do? In this section, we're going to go through a number of tips and techniques that will help you get the best results from the tools, help when debugging a design, and finally, and probably most importantly, help to close timing. During the process of creating an FPGA design, there may be parts of the design that are incomplete or not yet available. However, you want to still be able to compile the project to perform timing analysis and verify the functionality of the completed parts. When a design is being created by a team, this situation is even more prevalent. The problem is that without a complete design, normally you would not be able to completely compile the parts that are available. Even if you successfully compile what is available, the compiler may synthesize away logic that is connected to the incomplete or unavailable parts of the design. The solution is to, of course, use incremental block-based compilation, but insert black box wrapper files as placeholders for the missing or incomplete blocks. The black box can be set as a design partition with the empty assignment enabled after analysis and elaboration. As seen earlier, the connections to and from the empty block will be maintained, allowing the rest of the design to compile as if the missing or incomplete block was in place. Simply replace the black box wrapper file with the completed code or IP once it becomes available. Disable the empty assignment and recompile the design. Here are Verilog and VHDL examples of a simple black box wrapper file. All I/O ports must be defined, but no other logic is required. Again, once the logic becomes available, simply add it to the black box file or replace the file in the project. Another situation you might run into, but later in the design process, is the implementation of debug logic. Some debugging tools make use of device resources, such as logic blocks, memory blocks, and I/O pins. And if your design is using a large percentage of these resources, the logic for these tools might not fit in the device. Once again, incremental block-based compilation can help with this. If parts of your design are completely and fully debugged, you can set them as design partitions and temporarily enable the empty assignment. Remember that emptying out a fully compiled partition removes all the logic and routing used by that partition, freeing up those resources. With the resources now available, the debugging logic can now be implemented. Note that the logic that is being emptied out must be independent from the parts of the design that need to be debugged. If the functionality of the logic being emptied out is required for debugging the rest of the design, you won't be able to use this technique. The implementation of instances of the signal tap logic analyzer is the most common situation where this technique is used. The signal tap logic analyzer uses logic blocks to implement trigger conditions and memory blocks to store captured signal data. The more samples the logic analyzer is configured to capture, the more memory blocks required to store that data. If there is a completed part of the design that is using a lot of these resources, set it up as a design partition and empty it out. You can see how many memory resources are being used for each part of the design in the Design Partitions window, the Project Navigator, or in the Plan or Place Stage folders in the Fitter folder in the Compilation report. When you are done debugging, turn off the empty assignment, set the preservation level back to not set to recompile the emptied partition, and then switch the preservation level back to synthesized or final. You could also simply remove the partition designation to force the logic to be reintegrated back into the design. As a side note, if you don't want to empty out part of your design, you can make use of the RAM type option in the logic analyzer to specify which type of memory blocks it should use. Choose a type that is different from what you are using in your design. That way, the memory resources used by the logic analyzer will not interfere with your design. The next recommendation deals with periphery planning. Most designs involve one or more high-speed I/O interfaces that may or may not use the device's transceiver blocks, such as external memory or PCIe. These interfaces typically only use periphery resources, though some, such as external memory, may make use of some core resources depending on the options selected for the implementation. Once these interfaces are operating correctly, they don't typically change much during the rest of the design flow. As such, it's a good idea to get I/O interfaces working early in the design flow as part of the root partition or one level down in the hierarchy, and then lock them down. To do this, add black boxes for the core partitions you know will be in your design, or just one large black box for the entire core design, and enable each one's empty assignment. Remember that core partitions can't use periphery resources, so if they're emptied out, you'll get fast compiles for the periphery resources. Use tools such as the pin planner, the chip planner, and the interface planner, formerly known as Blueprint, to design the periphery. Once the periphery is complete, any periphery blocks can be set to final, and you can continue working on the core. Remember that the top-level root partition does not have a design partition preservation level, so the top will always be final. Let's finish up this training with a look at some techniques for closing timing using design partitions. There are two main ways incremental block-based compilation can help in closing timing in a design. First is through reducing the number of design compilation iterations. By being able to work on a small number of partitions at a time instead of the entire design, the entire process of timing closure is easier, requiring fewer compilations. Also, since you can make small bug fixes or RTL changes without affecting the rest of the design through partition preservation, again, fewer compilations are needed. The second way is through targeted optimization. By focusing optimization efforts on the parts of the design that are not meeting timing, the compiler can iteratively close timing on each of those parts until the entire design meets your timing requirements. Using incremental block-based compilation as a tool to help with timing closure is good for both top-down and bottom-up design methodologies. It is especially useful for true bottom-up methodologies because each team member is working on their own part of the design independently. Time enclosure on each team member's parts is important to help make sure the overall design meets timing when those parts are completed and added to the top-level design. To learn more about time enclosure techniques in FPGA designs, attend the Time Enclosure instructor-led training, linked here. When closing timing, it is recommended to try to get as much margin as you possibly can. Don't just try to get positive slack, try to get as much positive slack as possible. If 200 MHz is your timing requirement, for example, 205 MHz meets your requirement, but it may not be enough margin when changes are made to the design later, or if the design may be integrated with other design blocks. Performance can potentially drop when parts are integrated together. Obviously, project scheduling dictates how much time you might have to get more margin, but just try to get the most you can in the time you have. Throughout the entire design process, even in the early design phase, time enclosure should be taken into account. The sooner you include optimizations in parts of your design specifically for closing timing, the easier it will be to close timing in the overall design. It can be much more difficult later on in the process to close timing. You may find that a part of the code you haven't touched in a long time is having issues, and you may not be as familiar with that code. You may have created test benches designed for specific functional verification, but changes needed to close timing have potentially affected what those test benches are analyzing. Think about closing timing early and get the most performance out of your individual design blocks before you integrate them together. So how do you use incremental block-based compilation to help with time enclosure? The main strategy is through hierarchy isolation, the idea of isolating one or more target design blocks and focusing optimization efforts on those targets. The easiest way to do this is to set all parts of the design adjacent to the target block or blocks as empty. We'll look at what this means in a moment. After optimizing the targets to meet timing, you can then optionally remove the partition designations and compile the entire design flat to allow for all cross-partition optimizations. Adjacent design blocks refer to parts of the design that are near the target of optimization. They may be on the same hierarchical level as the target or one level up or down. You may just want to set other large parts of the design that are not directly adjacent to empty as well. The more of the design you can empty out, the shorter the compile time during optimization. This strategy of hierarchy isolation usually works best in a design with fewer first-level hierarchies because there are less branches of the hierarchical tree that need to be removed. However, it should work well in most designs where the design partition recommendations given earlier are followed. If parts of the design are already finished or the target blocks rely on an adjacent block's functionality, you might want to set their preservation level to final instead of enabling the empty assignment. Remember, when a partition is emptied, all of its functionality is removed. Setting a partition to final maintains design functionality and makes the compiler aware of those finished partitions. This allows the compiler to optimize the paths between the target and finalized blocks. Once the targeted blocks are isolated, they can be optimized independently. If all critical timing paths are located within a target partition, the partition can be set to final as soon as it meets timing, at which point you can then focus on other targets. If you have critical paths between partitions, both source and destination partitions must meet timing before they can be locked down. This is why it is recommended to keep critical paths within a single partition, as recommended earlier. Before going into the time enclosure flow in detail, it is a good idea to consider exporting design partitions that are meeting timing as .qdb files. This is a good archival process for saving completed parts of the design without having to archive the entire project. It's also useful for backing up a partition before emptying it out. Remember that emptying a partition removes all post-fit information for that partition, so it would need to be recompiled from source to bring it back into the design. Using a .qdb file as the source helps mitigate this. To be used as a source file, a .qdb file requires, at a minimum, an associated black box wrapper file. The Intel Quartus Prime software exported database files are used in the design block reuse flow to transfer design partition information from one project to another. Storing partitions as .qdb files makes them completely portable, including placement and routing information. While this information is available in a project's QDB directory, it is not as easily portable as a .qdb file. To learn more about the creation and use of .qdb files, see the Design Block Reuse online training. Here are the steps involved in closing timing on a design through design block hierarchy isolation. First, set the target block's preservation level to not set to recompile back from source code. Then, do a full compilation of the design. Using timing analysis and optimization techniques discussed in the Intel Quartus Prime user guides and related trainings mentioned, optimize the target blocks, recompiling as needed until they meet timing. While targeting only one partition at a time is recommended, you can save compiles if you can optimize more than one target block at a time. Once the target block or blocks meet timing, set their preservation level to final. Continue on to other target partitions until no parts of the design are empty and the entire design meets timing. In general, this methodology is good for design blocks that are unlikely to change later in the design process. As you go through the steps, the compiler is aware of the finalized partitions, which is good for optimizing the placement of each target partition as you optimize it. Now, while device floor planning is not required with this methodology, it might be difficult to go back and make changes to the design later. Floor planning indicates to the compiler where exactly in the device logic must be placed. If changes are made to the design, for example, and more logic is required for a design block, other logic might need to be moved to accommodate the extra resources needed. Floor planning can help mitigate this. To learn more about floor planning using logic lock regions in the chip planner, see the Design Block Reuse online training. Finally, besides or along with hierarchy isolation, you can make use of fitter effort. By default, the fitter effort setting in the project's advanced fitter settings is set to auto fit. This setting runs the fitter until the design meets timing or until the fitter decides that it can't both place the design and meet timing with the current design seed. The auto fit setting should be sufficient to close timing on design partitions that easily meet timing. Once these partitions meet timing, lock them down and change the fitter effort to standard fit. This will focus fitter effort on the target partitions, making the fitter run longer to see if it can select a fit that meets timing. Overall compile time should be reduced if much of the design met timing with the auto fit. Once more partitions meet timing, lock them down and continue the process until the entire design meets timing. This is a great way to easily close timing if no changes to RTL code are required. This concludes the final part of this training. If you missed either of the previous parts, you can register for them for free at the links shown here. To learn about additional resources available to help you with using incremental block-based compilation, continue to the next slide. For more information about incremental block-based compilation, be sure to read the Intel Quartus Prime Pro Edition user guide about block-based design, linked here. This should be your main source of information for all aspects of using the feature. The other user guides listed, and the chapters highlighted in each, provide additional information about topics discussed in this part of the training. Other online training classes, just like this one, are available. The classes listed here go into more detail on tool use related to incremental block-based compilation and the related design reuse flow. You can register for them and watch them for free at any time. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Visit the Intel FPGA Wiki for design examples and up-to-date articles written by field application engineers. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training about incremental block-based compilation.